discussion. Our speaker will be Balázs Sipos. Balázs Sipos is a lead developer for the AI OCC project at Lufthansa Systems Hungaria. He's a devoted full-stack developer with a wide range of experience on various projects and systems. Passionate about lifelong learning, Balázs continuously enhances his skill set, keeping pace with the latest technological advancements. A significant part of his work is dedicated to architecture design, focusing on creating robust and scalable project foundations. When he's not working, he likes cycling, gardening, reading, and hiking or tinkering with an occasional technical side project. The title of the talk, Taming Turbulence with Code, Developing AI-Powered Solutions for Airline Disruptions. Please welcome on the stage with a huge round of applause, Balázs Sipos.
Hello, everyone. Can you hear me all right? Better than how you hear the pilot during a flight? Then we are good to go. OK, so I'm Balázs Sipos. I'm from Lufthansa Systems Hungaria. And I would like to showcase to you one of our exciting projects that I've been working on in the last few years. But first, let me talk about Lufthansa Systems a little bit, as not many people know that there is actually an IT company behind the Lufthansa name, under the Lufthansa name. And we know this because there are a lot of people coming at us and still trying to buy tickets from us and trying to rebook their flights. And we're like, sorry, no, we can only make you suffer if you are in the aviation industry. So, yeah. We are situated in two places here in Hungary, in Budapest, not at the airport, but in Info Park, and in Szeged. And we are making aviation software. So I think when the first, you may have used our software during flight when you had like a longer flight, when you watched your movies, the entertainment. That's one software that we are making, or the software which assigns the crew to your flight. Maybe it was made by Netline crew, or if your flight was delayed, maybe it was made by the operation controllers who are using Netline Ops++. And this is where we get to my talk, because my project, AIOCC, is connected to Ops++. It's basically an AI plugin for that. And this is what operation controllers use. And you might ask, who are operation controllers? Well, this is where we start our little talk here. I will talk to you about flight operation controllers, what they do, what problems do they face in their everyday life, and I will show you a solution, which is our solution, AIOCC, and then we will go under the hood, how it works, and we will talk about reinforcement learning a bit, because that's what we use behind the scenes. And then, of course, a little Q&A session. So, flight operation controllers. Basically, they are responsible for smooth schedule execution, which means that they have to execute the schedule in a way that is good for passengers and for the airline as well. Passengers in a way that there is not much delay. The airline don't have to pay money for like hotels and buses and things like that. And in airline way, and for the airline, yes, for not to, it has to be, sorry. So they're working in two states. There is the bore-out state and the burn-out state. The bore-out state is basically when they have to do nothing. They're watching football because there's nothing bad happening. Like the schedule can do as it was planned. But the more frequent is the burnout phase, like when we have weather like this. So I don't want to be a flight operation controller on Ferihegy right now. They have to work really hard. They have to make really hard decisions in a short time span with a lot of information coming at them. They're working in shifts, and they are using multiple monitors, as you can see in the picture. Usually, then they have to distribute the work. So there's an airline has more than hundreds of aircraft usually, and the operation controllers distribute the work by aircraft or by home base. Homebase is like a hub. It differentiates between what is the airline. If it's a hub airline, then you can think of a Homebase as Munich or Frankfurt for Lufthansa. And what you see on the top screens, that's Ops++. Here is a bigger picture of it. So this is what we call a Gantt chart. You can see the schedule here. So on the right-hand side, you can see the aircraft number planes, let's say. And on the rows, you can see the schedule for one aircraft, and you can see the actual times as well. So there is a red line. That's basically the now line. We have like 5:30 now, and you can see these red rectangles, which says like that leg is delayed. And they are using this to make changes to the schedule and to operate. They have a lot of information coming at them. They have to make really fast decisions with a lot of information. And one of the information is like weather or the ATC regulations. ATC is the air traffic control. They are the guys up in the tower telling you when the plane can depart, or the maintenance events. Aircraft has a lot of issues with them, like you have to oil check, and I mean, there can be a puncture during landing and things like that. Emails, phone calls, a lot of other things. And also, this is the airline industry, so we really like acronyms here, but you don't have to really worry about it. We have a lot of more information that's coming in, like air traffic congestion. So if you usually fly during summer, you might have had a delayed flight because the European airspace was too congested. And this is what they have to take care about. Connecting passengers is really a crucial part of their work. But you can think of how can one human being do this kind of stuff. Like, they have a lot of information in. They have like 10 minutes to make a really good decision that would save passenger time, delay, and everything. And human beings are not really designed for this kind of stuff. So, but what we think a little bit, computers was designed this kind of stuff, like giving like a bunch of input to them and process it magically and get like a really good output. Yeah. So this is where our solution comes into place. What if we get all this information that makes the flight operation controllers confused, give it to an AI agent, and the AI agent would just give you a recommendation. Please do this action, and then the schedule would improve with this and that, and the flight operation controller could just accept it or reject it. That's the basic idea. Our basic concepts are that it's data-driven, so we are learning from the data. The day of operation, the day when the schedule is actually executed, is too complex to model it. So if you just going with the model-driven approach, we would need to make strong assumptions. And when we do strong assumptions, at the end we would optimize for the assumptions, not real life itself. So we were going with the data-driven approach. We let the ops controllers have the control because they are responsible for thousands of people's travels every day. And the tool is proactive, so it can learn. It can see issues before they come up. So if you just say an example, in Frankfurt, maybe the afternoon schedule usually gets crowded a little bit. So there's a lot of delay on these and that aircraft. And maybe the AI agent can see this because of historical data and training, and it can generate a recommendation. So if we would like execute that, we could save that afternoon schedule a bit. This is our UI. So we were trying to make it as comfortable as possible. They don't want to make a new box to them, so a new information source they have to check and see. Just a solution index which tells them how good the solution is. The action itself, so it's a swap recommendation. I will talk to you a little bit about later. And if we go down a little bit, here is the results. So we are trying to explain to them why is this action actually good. So if the AI agent says the answer is 42, we have to somehow explain to them why is it 42. So we are saying things like the delay is decreased, the buffer time is increased, and we also show like possible issues. There are some business rules in the airline business that is just not in the data, it's in the head, and it's some documentation of the operation controllers. So we can give them as rules, and we can show them. So here we have this NEO versus CO efficiency. It basically means that NEO aircraft, it can mean that the NEO aircraft is much more silent than a CO aircraft with Airbus. And there are some airports like London Heathrow who really likes NEO aircraft because they are silent, and the airline have to pay more money if they are actually flying there with not a NEO but a CO aircraft. And after the operation controller accept or reject the recommendation, they can give us a little feedback. And with the feedback, we can evaluate and make the tool better. So what the two-way swap actually is, I just want to show you what actions can you actually do with the schedule. You can't really put a leg a little bit before, as the passengers will not be on the airport. So what we can do is do a little swap. So we have one aircraft here, Lima Victor Echo and the Lima Charlie India. And if we do a swap, I can't go there really, but from Vienna there is like two rotations. The rotations like from Vienna it goes to Oslo and then comes back to Vienna, and the other one goes from Vienna to Barcelona and comes back to Vienna. And if you do a swap here, you can see the bottom aircraft is delayed because of a bad slot. It basically means that the air traffic controllers doesn't give us a good time window when we can take off. So it can actually delay the whole schedule of one aircraft. But if we have a good swap like this, we can make save like 20 or more than 30 minutes, 40 minutes by just doing this swap. So we would get the legs from here, put it down here, and get the legs from here and put it up here. And this can be done because on the first aircraft, the rotation starts later a bit. This is one action that they can actually do, and what we recommend them most of the time. So let's check under the hood a little bit. So this is the system context diagram. You can see the operation controller there, and we have netline ops++. And the operation controller uses ops++ as he usually does, and checks the ALCC system for recommendations. If he or she accepts a recommendation, it goes for ops++, and where they can publish the change. And when they publish the change in ops++, it goes to other airline operators like the crew people, the maintenance, and the airport, and everything. We also have an AI expert here who can fine-tune the agent for the airline's need and give like more rules to them. Our technology stack is that we are Python and Java microservices. Python, surprise, surprise, because of AI. We have an event-driven architecture because if something changes in ops side, we have to react to that. And we use event sourcing, which I will talk to you about a little later. We use a modern web UI in React, and we use change data capture for the connection to ops++. We use Debezium for this. I don't know if you know Debezium, but it's an open source Red Hat project. We even have them a little bit. It's a really nice project. So basically, change data capture is a way to get data from a relational database in a way that it doesn't make any performance impact. It basically checks the database. It's not querying it, but checking the redo log if you're talking about Oracle, and it generates message events on the changes of the database. So, event sourcing. How many of you heard about event sourcing before? How many of you used it? Some people. Yeah, it's not really. It's not an easy architecture, but it's really nice in some cases. So it's basically a pattern for storing data in an event-only log, append-only log. And let's say we have a business object leg, and on a relational database, we save it as a leg row. But in event sourcing world, we not save the object itself, we save the events that happening to that object. So if we just get a new leg from ops++, we have a leg created event, and if the ops controllers give them a PAX, then we have a PAX added event. If the leg departs, we have a leg departed event, and when the leg arrived, and we have another event. And it's really easy to see why this is good. We have the whole life cycle of the object we can see. We can really easy debug the system this way, and we are able to travel in time, which is really crucial for us because with the AI agent and everything, we can just travel back in time, evaluate the situation, see what the agent recommended back in the time, and actually train the agent, because this is how we train the agent as well. There is some drawbacks, of course, like performance. Like if you want to get the leg object to make your business logic, do you have to really always go through the events? Well, yes, but you can use snapshotting. So if you do a snapshot of the leg object, you have to just rerun the events from the latest snapshot. And of course, using CQRS and read models and things like that can really help in this matter. So let's check the AI part. So we are using reinforcement learning. I think everybody heard about reinforcement learning before, but if not, I will talk a little bit about it in a nutshell. So we have an agent down there, and we have an environment. Reinforcement learning is basically mimicking this trial error learning method that babies do, and we all do actually when we are raging on a code and nothing's gonna work. We have the agent, and we have the action and the environment. So the agent do an action, which changes the environment. From the environment, it gets back a state and the reward. So the reward is telling us how good the state is that the agent get in. And if you just think about the game chess, we have the agent, who the player, the action, the moves that he can do with the pieces, and the environment is the board itself, and the state is where the pieces are, and the reward is, let's say, is how far the agent is from winning. You can formulate this a lot of other ways. The reward itself, it's really a crucial part how you calculate the reward. But you must think that reinforcement learning is really good at gaming, like in the gaming world, because you have access for the whole environment. Like basically, you coded the whole thing, you have the game, you can do any situation as you want. But in real life, let's say the day of operation, it's really hard to simulate this. So maybe with quantum computers we are able to do that, but we are not there yet. So we can't really use this exact method, but we can use some part of it. So what we are doing is train the agent to be able to tell us how good a situation is. So if we get him, let's say, a day of operation schedule, like you saw it at the beginning, give it to the agent in a tensor form, we will just get back a reward, like 42. And to go back to that example. And what we do is basically creating our own actions, like a two-way swap, because the actions are complicated itself, and the agent wouldn't be able to just figure it out, and because there are a lot of rules and things that not in the data. So we're generating an action as well. We change the state, and we give the state again to the agent to ask what the reward is. And if it's 44, then we can see that the situation improved. And we can use that recommendation and show it to the operation controller. That's the basic idea. Next to this, we have also rules, as I was talking about. We need the rules because, as I said, not everything is in the data. And so we have feasibility rules, which is in the ops itself as well. So when the operation controller do something to the schedule, we can see if anything goes wrong. So let's say if you have a leg from Budapest to Vienna, and after that we have a leg from Munich to Toronto, then we can see that from Vienna, we can't really go to Munich without flying. So we can't really taxi the plane there. So it would be a feasibility exception. We couldn't really do that. And This is one of the area of rules. The other is the soft rules, which is basically tells us the preferred and not preferred actions. These are made by the airline itself, so this can be different from airline to airline. So they give us the rules, we put it into the system, and they are like rules like that you saw the CO versus NEO example that I told you about. And we show it on the UI like a possible issue or like a plus, like avoiding a curfew violation and things like that. We also have action feasibility, which is basically another hard rule, so we filtered recommendations out with this, but this comes from the airline itself again, and these are like swaps. Let's say, for example, a swap is not allowed with leased aircraft, which basically means that the airline has their own aircraft, but also they lease aircraft sometimes. And they cannot really make actions like two-way swap around this area, so they cannot swap with their own aircraft with the leased aircraft usually. So this is really allows us to have really flexible AI architecture, so the agent learns the situation and the rewards, but not the action itself. So we generate the action ourselves, and we can easily add new action without touching the AI part at all. And we can also change the goal function without changing the neural network and the transformers under that. Yes, sorry, this is pretty much it. So, thank you for listening, and I think I was too fast. Yes, I was really fast, sorry. But if you have any questions, please ask away. I will do my best to answer.
Q&A time. Here's the QR code. Feel free to scan it and send away your questions. We already have a couple, so
good.
You guys have time to send lots of questions, so here's your chance. But in the meantime, let's get rolling. Number one, do you only provide these applications to Lufthansa?
No, we actually have a lot of software that is for the airline industry, so not just Lufthansa, but other airlines as well.
Number two, is it a recommendation only, or can it do fully automatic decisions?
It's just recommendation only because, like, the operation controllers like to have the control still, so they don't want to. They don't want an AI agent to just do things to their schedule without any supervision. So we are not there yet.
All right. How do you measure improvements?
Basically, we have observability. So what the agent do, we can see from these heuristics like the buffer, propagated delay, and a lot other how good the recommendations are. We see how many recommendations are accepted by the operation controllers and what their feedback is. So if they reject the recommendation, why did they reject it? And yes, of course we are working on a solution where we would re-evaluate a historical day and try to do recommendations there because of the time machine thing. So we can see without human supervision what would the agent have done in a really difficult day. So if we would accept every recommendation it recommended, how the day would have ended and things like that.
The next one is also about improvements, but before we move on to that, you still have time to ask questions, whether at home or here. Be sure to live with the opportunity. So the next question, do you get feedback from passengers? And are these improvements even visible for them?
Well, for passengers, it's not really visible. So maybe you can only feel the delay or that your plane wasn't delayed. So you can't really see what's happening behind the scenes. That's why it's good to work here, because I can see some background knowledge. Like if I'm at the airport and I'm traveling and I see a delay, I can say, okay, maybe I am the unlucky one that was swapped to a wrong aircraft, but some other hundreds of passengers now can fly freely. So yeah, it's good to see back into to the behind the curtains. Yeah.
All right, cool. Okay, questions are coming in. Next one is from Daniel. Can you think of using the model for similar optimization problems? Example in crew management or scheduling.
I think there are projects that are happening in Lufthansa systems. They are trying to utilize AI much more in different areas as well. But this is the first area that came up because it's a really crucial area. So yeah, it can happen.
All right. How many AI recommendations can the operations reject before making their own decision?
I'm not really sure with this question. I mean, they can do their own stuff still, so they don't have to just accept and reject. This is just a supporting tool. So it's for they can still do their own job, and if there's a good recommendation come up, they don't have to always just see the schedule. And I don't know, we are always thinking about, okay, they can watch more football because they watch the football match and the new recommendation comes in, okay, accept, okay, watching further. So this is the idea.
All right. Potentially the last question, we'll see about that. How reluctant are the airlines to use AI?
It's different. Like some airlines really want to improve and get better, and some airlines are really slow in this matter. So, and also the users. Like if we have a young operation controller who wants to change the world, he much more frequently uses the tool. But there are operation controllers who are on the field for 30 years, and they say, please, a machine won't tell me what to do. So it won't really use the tool.
Okay. Our first potentially last question is usually not the last question, and this is what happened now as well. Now the questions are coming in. What kind of cloud infrastructure do you need to run a system like this?
Well, it's not really. I mean, training is a heavy part. It needs a stronger machine, but running the application itself is not that heavy on the processing power part. We can easily scale it. It's running in its own microservice, so we are generating the situations and we're giving it to the agent to reevaluate and get back the result. So it's happening in like 20 seconds, and so we are trying to be as close to real time as possible because being far from real time means that it's not really a useful tool because the operation controllers need to be at the moment, always.
Would it be any good for trains or even buses?
Well, yeah, I think it can be. It can be because, like in OS++, there are some airlines who use it for buses as well. So, so it can happen, yes.
Okay. You mentioned a couple of domains like crew assignment, scheduling. What would you say is the most complicated?
Well, from what I heard from the colleagues, the crew part is really complicated. I haven't really worked on that part. And also, the OS++ part is complicated as well. There's a lot of business logic behind that, that area. And also load that I heard, like you have to calculate it with netline load, the optimal way how to load the aircraft. So where to put the baggages, where to put the cargo. So the center of gravity would stay in a good place, and it wouldn't make any issues during takeoff or landing. So yeah, that's another hard part, I guess.
Attention passengers was very adequate for this topic. We have lots of more questions coming in. Awesome.
I knew I had to go fast because
yes, you felt it. You felt it. You just let space for people to ask what they actually wanted to hear about. Next one, what's the approximate ratio of recommendations being accepted and rejected?
Well, it's sometimes good, sometimes bad. It's really, I don't know what it depends on. So, I mean, maybe who uses it, who's in the shift. So we had some months we had like 40% acceptance rate, and now we are down like 10. So it's not really possible to know.
Okay. How much time does it take to implement a solution like this?
Well, the first proof of concept was done before COVID. I think they were working on for 2 years. 3 PhD dissertations were made during the development as well. And after that, we made the product from it. So we started at COVID in 2021, and now we are at already at the customer. So, yeah.
So are these ops controllers employed by the airlines or the airports?
They are per airline, yes.
Okay, that was a quick answer. Any plans on replacing Oracle? The question's from Daniel.
Yes. Yes, it's already replaced actually. I mean, a lot of customers still use Oracle, but our system, OS++, can use PostgreSDB as well.
Okay. I think this is breaking the record of potential last questions, because there's a new one just came in. How big is the team working on this?
Right now, I mean, when it started, they were a lot of data scientists on it. They were, I don't know, 3 or 4 data scientists. And now that we are making a product of it, we are 5. Yes.
All right. Maybe this potential last question was the last question. Any other last questions? I'm trying to look at the phones, which you never know for sure if it's for this or for something else. All right. Well, then, in this case, thank you so much for the presentation and the answers.
Thank you.
A huge round of applause. Thank you. Thank you.